Welcome to the talk. So I'm having a talk about the command line version, so to speak, of Wireshark, which is T-Shark. And who of you did ever, for whatever purpose, use T-Shark already? Okay, that's quite a lot. Can you give me a few examples of when you had the need to do it, or was it just out of curiosity if you could do something with it? So what's your typical use case of switching from the graphical interface to the CLI? Anyone? What again? Okay. Using what?
I was using Kali on that.
Okay. So when you're already on the CLI and just want to be quick and fast about it, right? Okay, so I'm not trying to convince anyone to switch and go away from the GUI and stick to the CLI. So this talk is not about some typical use the CLI talks because it's like cooler or whatever. So I just want to differentiate because there are certain use cases which you can do perfectly using classic Wireshark and the GUI, but there are some things which you can do maybe a little more efficient or maybe a little more performant using the command line. So this, in general, is what the talk is based about, right? So I'm giving you a short outline, so I won't cover the full command set of the T-Shark command line executable, but I want to give you the most important flags that we use in our day-to-day work. And as mentioned, we're going to have a few demos, or lots of demos, where I said this, for me and for Jasper, working in our network projects, is the most useful situations switching basically to CLI. And by switching to CLI, I don't mean doing everything with T-Shark, because there may be other CLI tools which can do the job, but I just focus on T-Shark because I want to give you all the options to do it with that tool. There may be other variations which can do specific tasks slightly faster or slightly better, but T-Shark basically does everything you need in terms of doing the stuff which I'm having the demos about. So one of the big parts will be also batch jobbing. What I mean with batch jobbing is coming to be on the next few slides. Just as a quick intro, we used to work with at least 3-digit number of gigabytes of traces in our projects. So when we go to a customer site and we hook our sniffer up for at least 24 hours to a few days or even a week, we don't get back with a nice, small and easy to read trace file with a few thousand packets, but we end up like having 600 gigs of data, 1.5 terabytes of data, 3 terabytes of data whatsoever. And that definitely is the point where you don't want to open every single trace file in Wireshark, scroll through it, search for something, close it, open the next one, and do this for 7,000 plus traces. So that's at some point where an automated batch job comes in, where you need to have some scripted tools to just get the job done, leave it running overnight, and take a look at the results next morning. And one of the most important features I'm going to pinpoint this demonstration on is the ability to extract data, so specific pieces of data out of a trace file. Who did this before with T-Shark? No one? Just a few? Okay, so I think this will be very useful for you. By the way, who's doing the packet challenge? Okay, those of you who don't, maybe you should give it a try. It's quite interesting. And just as a hint, I'm not going to solve the questions for you, but exactly this data or field exfiltration feature comes in very handy when solving various packet challenge-like examples and stuff like that. And for those who know me, it's not going to be as much slides, so I will be most of the time sitting on the CLI or inside some traces. So please excuse if not everything is in PowerPoint. Okay, so let's get started. Basically, when you fire up the T-Shark executable on your CLI and just append the -H, you get all of the information available with all the flags available for T-Shark. And as said, I'm not going to get through all of that, but you can just fire up Google and say T-Shark man page, and you will get a pretty detailed explanation of all the single options you have there. And since T-Shark basically more or less is kind of the CLI alternative of Wireshark, you can imagine that all the stuff you can do in the graphical version, more or less, can be done using the CLI. Of course, you need to have to be willing to use like 3, 4, 5 line long commands, but that's how it is. But I strongly recommend you to just take a sneak peek at that and see if you can find some useful options in there. It's, like said, the most important ones we're going to cover as of now. So, a few things to say about the command line environment. So when you use various profiles with Wireshark, you can use the GUI to switch around these profiles, and as you may have seen also in Hansang's talk, everyone has different graphical interface profiles. So if you start using more than just the default profile, you might ask the question, what does T-Shark do? So is there any way to specify T-Shark to use a certain profile? And definitely it is, because the T-Shark executable by default sticks to your default Wireshark profile. So let me show what I mean with that. So I have this Wireshark open with some file I downloaded just this morning using the Wi-Fi here. And with all your profiles, the default profile is what T-Shark is going to use. So whatever you have configured, for example, as the columns, meaning default time, source destination IP protocol, etc., this is what you'll see on the command line. So I added to my default profile, as you can see here, like delta time, cumulative bytes, and the absolute time. And when I switch to the CLI and make him read this exact trace like we have in the GUI, you will see that all the information, so relative time, source IP, destination IP, etc., comes up. But in the end, which is a little small here, so let me do this again. So you'll see down here, I have here 66 and some 2016, 14th of June. So this is my cumulative bytes and my absolute time. So whenever you're missing information on the CLI, you can either manually try to add those using various commands in T-Shark, or what I would recommend is you just build yourself some like CLI profile where you just conveniently apply all the columns you want to have, and then call this profile on the CLI, because that's everything you will have available then in text form, basically. Okay. So why use the CLI? It's not that much that it gives me everything I need, but the good thing for me is having information from the trace passed to standard out through Wireshark gives me the ability to post-process all the text output I get from analyzing the trace. So I'm not talking about having nice statistic information like the I/O graph, for example, or anything else, because this is something I clearly do using the graphical interface. But let's say you have a list of IP addresses and you want to just search something in or grab for a specific IP or use string alteration tools like cut or replace with SED or something. That's something where having the command line ready to go comes in perfectly handy. Of course, you could also extract what you see in the graphical interface to a CSV file and then process the CSV file, but as you will see, this is way easier just focusing on T-Shark and limiting it exactly to the fields you're about to need. So if you don't have a clear understanding of what I'm talking about, don't worry, we'll have lots of demos like after the next 2 or 3 slides. So with T-Shark, you can also basically just fire up a quick capture, and it does exactly the same like the graphical interface. So once you say, T-Shark, please capture my traffic on a specific interface, in the background, it will fire up the dump cap process, which takes care of all the stuff. So again, I'm not saying you should not use the GUI and capture with T-Shark, but it's just an additional thing which you, of course, also can do. So if you go for T-Shark with an uppercase D, you'll get the interface listing. In this example from my Windows machine, where you see all the GUID identifiers of my different network card interfaces. And if I'm about to capture, let's say, from my current Wi-Fi interface, you just follow the line and see, okay, this is interface number 4. And so you can just go and say, T-Shark, go capture interface 4. And as soon as packets are coming in, if I do something or just wait for something to happen, you should see them there. There you go. So basically, that's nothing else except for on the GUI just firing up the Wireshark and having him do something, right? So as one of the first things, if you're not interested in detail about the packet dissection, but let's say you just want to check, am I sending or retrieving, for example, DNS packet, you might try to add a filter and say, please grab me all strings containing DNS, and when you visit whatever website, there you see on the text output, you see the basic packet list line from Wireshark filtered for the DNS string to appear in that. Of course, you could also use a display filter, but just to give you a first expression of what might come in handy for one or the other situations. Good. So, when does it really come in? I've already mentioned before, when you end up having big amounts of data, we usually go for doing a ring buffer with multiple files instead of one big trace file. Does everyone know the concept of the ring buffer, how it works? Or does anyone want to have a quick explanation about that? All set? Okay. So usually what we do is we choose to go to a capture file size between 50 and 250 megabytes. There's no fixed reason behind that except that I like them to be opened really fast. So if I end up having like 10,000 capture files, each like 200 megs around that, that's a size where I just need to wait a few seconds to open them in the graphical interface, to search for something, close them again, sneak peek in another file. And just my personal feeling that I like to have that more than having like 1 gig or 2 gigs of trace files where I have to wait 1 to 2 minutes every time I open the file. So it gives me the feeling that I can just work quicker in that. But that's just a recommendation from our side. So when you go through filtering data out of various traces, or even or especially over a long period, you can of course use the graphical interface, like going through the first file, let's say filter for some specific packets, like sticking to the example DNS or HTTP or whatever, and save the result to a new trace file, open the next file, filter again, save it out, open the next one, filter again, save it out. But as you can imagine, when you have like thousands of files, that will take ages, and that's where we want to use the T-Shark alternative to script this stuff, right? So the typical thing is when we have a bunch of huge piles of data, we do some pre-selection of typical things which are of interest for our up-to-come analysis. And by that I'm talking, we don't know yet what the problem is, so we just have a bunch of data and some problem description. But there are some things we always kind of filter out by basic before we start, if we have like a terabyte of data or more. And this, for example, might be, I'm not saying this is what you need, but this might be the whole TCP session flags. So if you have a subset of all the data just containing the SYN flags, the FIN flags, reset flags, whatever, you end up having maybe 3 to 4% of the capture size. So if you start with a terabyte of data and you just filter all the stuff out, you may or may not end up having just 1 or 2 gigs containing only the flags describing all the connections you have inside this huge data pile. So what's the benefit of it? Well, then you have something which you can, again, quickly process, quickly search through it. So if you're looking for a specific connection, if it has been set up, when it has been set up, and all the metadata around that, that again speeds up the process, and you don't have to go through all these thousands or tens of thousands of files. To give you a rough number, we recently, just when we did a project where we had close to 4 terabytes of traces, and whenever we had to do a full run because we were looking for something new, which we didn't do before, so we had to process like 7,500 files of data, each I think 250 megs in size or something, but this ended up to run like 10 to 12 hours. So whenever we found something new, which we didn't spot before, it was always going back to the start, waiting for the evening to come, set up the filter, and have the batch run for another 10, 12 hours. And as you can imagine, this is going to really blow your time in the project, and you can do this maybe once, maybe twice, but if you end up having like 20 new inputs and you're going to do 20 new runs, you're going to spend at least 1 or 2 weeks just for processing time, sitting there to wait for the data to be carved again and again and again. That's why we just recommend pre-filter as much as you can do, so we have the ability to quickly look up stuff. And pre-filtering is kind of pretty easy. So you go with T-Shark with the lowercase r for reading a file, and then with the uppercase y you can apply any usual display filter you know from the GUI. And once you did that, you can immediately have Wireshark or T-Shark save this PCAP with the remaining packets which are still matching the display filter with lowercase w to a new trace file. Right? So if we go here, back to this thing, and let's say, for example, we filter for TCP flags SYN, and we see there's just one SYN and one SYNAC. And we could go like File, Export Specified Packets, and just save those 2 packets to a new capture file. So this is exactly the process what we can do using T-Shark. So we go for T-Shark, please read this file. Please filter for tcp.flags.syn equals 1. And before we write it, we can just fire up to check, do we see something? And yes, we do. So here's our SYN and our SYNAC. And then we go and say, please save it to syn flags.pcap.ng. And then it's done, and we have this new capture available and can work with it in Wireshark, right? So basically, that's the idea behind that, to have T-Shark by a script go through every single trace you may or may not have, append whatever type of display filter you want to have, and save it out. I already said beware of the profile settings, and you can use any profile you already configured using the flag we have here, using the uppercase C. So for example, if I go to my default profile and say T-Shark, go read this file again. Now I have this column set here. If I want to change my profile to something else, I could just go like uppercase C and then look into Wireshark what profiles I did already do. So for example, I could use a classic profile and say, please use profile classic. And there you see I stop after the info column. So if I scroll up a little, you see in my personal default profile, like you saw, I have cumulative bytes, I have timestamps and everything, and in the default classic profile, it ends right after the info line. So this again gives you the ability to tune what you get out and what text is being displayed. So let's switch back here. So what I always would recommend is that you build yourself a custom so-called CLI profile with whatever name you give it for two reasons. One, that you always have the information in it what you want to have while carving out. And the second reason is there's various things inside Wireshark which can slow down the process of Wireshark or T-Shark being able to read the full packet list, extract information, and save it to a new file. So what you can do is you can try to tune the speed of the T-Shark process by disabling all the dissectors of the protocols you basically don't need. So if you're going for some basic TCP analysis, you could try to disable all fancy protocols which you just don't care, which are not in the trace, and get a little percentage extra speed out of that. And another thing, for example, is if you're doing database lookups, like for example geographic location. Geographic location takes a huge amount of time because Wireshark and T-Shark always have to take every single IP, look it up against a static database to determine where does that IP originate. Let me quickly show you how this looks. So for those who haven't seen that, if you enable GeoIP profiling, I have additional data, for example, here in the end giving me the geographical source and destination address of the IP address I have in the trace file. So while this might be nice if you're doing some forensics approach to see, okay, where does my data flows go or where do I get packets from all over the world, this definitely is something which slows down the process if you're just taking care of troubleshooting and you don't really care about all the information like GRIP, for example, gives when you look at the dissector area, because all this information, like where does it come from, which country, which provider, etc., this all has to be looked up from the IP address, and disabling that just gives you intense speed on the command line. Good. So, everyone good up to here? Any questions? So if you have questions, just feel free to raise a hand and interrupt me. I'm totally fine with that.
I got one for you.
Yep.
Have you noticed a performance benefit where you want to use T-Shark or TCP dump versus T-Shark for capturing close to line rate or when that's sort of bottleneck?
If you go and filter just for several hosts being inside a trace file, so you have lots of hosts in the trace and you filter out just the communication from single hosts or two single hosts, I would personally think that TCP dump will be much faster since it's not relying on the display filter syntax but using BPF filters. But it all depends on what use case you have. So usually when we're using T-Shark for doing that, we're somewhere in the dissector to just get random pieces of data out there, which I'll show you in a minute. And for me personally, that's easier doing that with T-Shark instead of TCP dump, which you may or may be not able to do. So.
Specifically for captures, you probably leverage TCP dump, especially if you're close to line rate. Is that what I'm getting?
Depends on the time. So if you're fine running 1 or 2 minutes more or 1 or 2 hours more, there's no need to do that. But if it really comes to performance, you have to just check what's quicker. But usually T-Shark is not that fast. That's what I meant in the beginning. It's not the fastest tool, but it just has all the options available, which I, in this case, focus on that. So I would personally always try to do a little benchmark, and when I have something which is way faster and I need the time, I switch the tool. Yeah.
I would say just Google Jasper and dump cat, and you'll get as long motion of line dump cat is faster than
Good. So in case you want to change some of the settings and you did not have a special profile for that, there's also, of course, the option to specify every single piece of setting which is available in the Wireshark preferences by giving it the lowercase o flag. Did anyone ever take a look in the preferences file from Wireshark? Yeah, Saki, you did, obviously. So let me quickly show what I mean. So if you have this trace file open, you might see when you take a look at the very top that I have the long sequence numbers and long acknowledgement numbers, which is because I, by default, don't use relative sequence numbers. You know, relative sequence numbers is a kind of easy-to-read feature where every single TCP session starts all over, and Hansang is laughing because he's, I think, also using that, and it starts all with basically back to 0, back to 1. So if I'm now using my default profile and go to the T-Shark CLI and just go for reading this trace, oops. Of course, what I get is, again, the long numbers. So if I'm not interested in that, or I want to match against a certain filter, so give me all the packets which have a sequence number of 1, for example. So I want to go for the relative sequence number. I have two options. So either I go back to my profile, and I go for a TCP packet, go for the dissector or for the protocol options, and in the protocol preferences, search for the relative sequence numbers and just hook that on. Because if I do that, and now it depends on if you close or restart Wireshark, but usually it should get it immediately. Okay, well, now it doesn't. So if I would close and restart Wireshark, it would update my profile and I would have that available. So, but this might not be as comfortable because you're constantly changing a profile, and the reason to have profiles is you don't want to change it all the time, right? So you want to have static profiles for various use cases, so I'm going to switch that back and disable the relative thing. So there we're back to normal. But one neat trick you can do is you can go for the whole protocol preferences page, and when you go for that entry you want to have, you see in the mouse over, unfortunately, maybe I can zoom that. No, then the mouse over goes away. Hopefully you can see way down there, you see a name tcp.relative_sequence_numbers. So that gives you a hint of the setting name inside the preferences file of Wireshark. And with that, you can manually go on the command line and say, I want this setting to be true or false, for this example where it's a just regular Boolean setting, right? So this is what we have here, like on the slide, where you say, okay, tcp.relative_sequence_numbers can be set to true or false. And let's try that using here. So we go lowercase o, TCP sequence, relative. So now you say I'm back to sequence 0 relatively. Right? So that's the quick and easy way to change it. I choose sequence numbers because it's pretty obvious. There may be other examples where you need to change a setting on a certain profile, for example, to track TCP timestamps, to be able to have delta times inside TCP flows, to enable or disable TCP Stream Reassembly when you're tracking like response times for higher layer protocols. We're going to have a few examples of that, but basically that's always the default way of switching that. So if something's itchy and you know it's a preferences setting or protocol setting, you can always like hard code the line inside the script to do it that way. Another advantage of doing that is if you just do a write down of what you did to process a trace, this kind of makes sure that whoever you give the trace to and whoever you tell, okay, I use T-Shark to do this, you will have the same settings for the profile, so you will get the same results. Because as you can imagine, if I use my default profile and run a T-Shark on it and give Jasper the same trace and just a T-Shark command and he runs it with his default profile or Hansang uses it with his default profile, the results will be completely different on the CLI because it just prints what's on the screen. And that's just a way to make sure for your own nodes in case you turn the project back to your desk like a year later and you wondered what have I been doing, how did I get to the numbers and the values. This is kind of good for documentation value and if you collaborate with other analysts to make sure this were the settings involved in that particular thing. Or of course you just pass the profile. Good. So to make things a little easier, oh sorry, yep.
So similar to the option flag setting the preference, is there some sort of flag where you can define columns?
I'm not sure actually. Does anyone know if you can specify columns in the preferences? You can? How?
There's an option in the preferences that defines the columns.
Let's check.
Look for column.
It's the only one? So I see the hidden columns, for example.
It's the setting GUI.column.format.
Ah, here we go. So maybe here. I didn't try, to be honest. Make like that.
You can set that on one line as well, the minor option. It's more difficult when you're setting it within a profile.
Does this answer? Okay, good. This is a typical example where I would take the task to create a profile on the GUI, set it, and use it, right? Because of these syntax-based issues. Okay, so for processing a large number of files using, here in this example, classic Windows CLI, of course you can use the regular Windows for loop to make it just run through all the PCAP files and do the static T-Shark filtering of the stuff you want to have, write it out to a new trace. So to do an example, I provided a ring buffer, hopefully. So I just captured like a few 10 megabyte files to speed up the process because I didn't want to have you sit here waiting for 2 hours to finish. And since the ring buffer comes in quite handy with the same names attached or postponed by the timestamp and the date values, you could go for all the files in this folder, or we say which start with the name dump. And you could go, please do T-Shark read those files. And if I fire that off, T-Shark will just scroll down through every single of those files. So now we can apply some filter, for example, DNS if it's in there, hopefully, to stick to the example. Fire that up again to see if it's working. And when I stop that, you see, yep, it's opening the first trace file, filters it for DNS, and you get all the DNS results from the first file. We go through every single file of those. So as a last step, I'm going to make a new directory. I usually call that filtered, so I know whatever is in there is not the pure data, but something I intendedly filtered using T-Shark, so it's only a subset of the original data. And so I now do, okay, go through all the files in this folder, throw on T-Shark, give it that file, filter for DNS, and most simple case, just write it back again with the original file name or with DNS only as an example, and then the original file name, and make him do that. So that's basically what I was referring to all the time. And as you can imagine, having many files, huge files, this of course won't just take a few seconds, but that's when you leave the T-Shark running overnight. And when we take a look at the results, we have that. Ring buffer filtered. So we are, right? So from our 10 megs of data, we're down to a few kilobytes. And just imagine this might have been way more for the loading time, but since ease of doing that, you can now mark all this filtered stuff ideally. And if you open up a new Wireshark, and the data is small enough, you can just drag and drop all the filtered data, and now you have all the DNS packets from the whole bunch of original traces merged into a single file. And now we can, from file 1 to file 17, 18, 19, through the whole capture time, scroll and analyze on the output, since this hopefully is small enough that it fits into a single file, which can be quite easily opened and processed in Wireshark. So you got the idea? Good. So in the real world, when you're having like a terabyte of data and you start filtering it down for DNS, for HTTP requests, for SYN flags, for reset flags, for FIN flags, you may not end up having one file merged with the results all together, which can be opened in 5 seconds. So you maybe still have a few gigs of data, still tens of millions of packets. But then again, you could use the new database to do another filter run, of course, and maybe separate by sessions, separate by host IPs, separate by protocols, you know. So this is kind of your own personal strategy. I personally prefer to do one big filter run using everything which may be of interest for me. So, for example, if you're doing a response time analysis of a web application, you definitely want to use DNS, HTTP, you want to use the TCP connection flags, you want to have other errors like maybe spanning tree protocol sources or whatever, and you end up having a big pile of data, which maybe not perfectly small to analyze, but it will be smaller than the original because you already filtered. And from that subset, you can go in a second run and maybe use the first half of the filters. So get off all TCP flags, and in another run, do all the protocol things like DNS and HTTP. And then use a third run to separate DNS from HTTP. So a little like divide and conquer strategy, and every run will be faster than the last, and you'll end up, hopefully, after 1 or 2 days, having all the data nice and softly separated by protocols, by IPs, by whatever you want to have, ready to process inside a single Wireshark window and search for it and spot the stuff you want to see. Okay? Well, that usually differs from case to case, obviously, right? So if you want to do this thing in a batch script and write a small CMD or batch file where you just want to have some stuff noted for future projects and you want to just remember how did I do that, just remember when using Windows especially, you have to do a double person sign instead of the single person sign if you don't run it from the CLI but put it in the script file. I don't know for what reason, but that's been there in Windows for all the time, and just keep that in mind and it will run pretty good. Good. Any questions up to here? So let's get started. Now we come to my personal favorite of using the whole thing. So whenever you filtered something with T-Shark, there's a new added command after the filter flag with the uppercase Y, which gives you the ability to extract certain values. And this is all started by telling the T-Shark command Tfields. So Tfields brings you to a subtext level where you can pinpoint every single value available by a display filter through Wireshark. So in this example, we have Tfields and then lowercase e with IP source and lowercase e with IP dest address. And if you know those display filters, you know what this is going to do. So it will just pop out the source and destination IP address on the CLI output, not the times anymore, not the frame numbers, not the info column, so just focused on this information. So let's check this. So I go out of the ring buffer again, use my syscontrols file again. And now go for Tfields, IP source, IP dest. And there you go. So while this may not make sense in terms of what shall I do with an IP list, I totally agree, it's just an example. This is how you can pinpoint every single piece of information inside a dissector. So whatever you're interested on, when you take a look on the GUI version, and for example, you open a field and you say, oh, here's a server hello, for example. See that? Is that big enough? Good? Okay. So if you go to the SSL dissector, for example, and take a look at the record, you see the handshake, and you see there's a server hello, and you have session ID length and all this stuff. And whatever thing down here you want to filter or you want to grab out of the file and print it in text, you can always go like down here and see, for example, session ID length is 0, and you see the display filter for that always on the very bottom left of Wireshark. So you could go like ssl.handshake.session_ID_length, give this to Tfields, and he will just print this field into the text file. Yeah, so, with anything in the dissector, if it's precisely described by a display filter, you can use Tfields to dump this value out on the CLI. So let's do a few things where I hope you get an impression of what you can do. Oh, before we do that, there are certain certain types of data where you may have multiple outputs out of usually single field. So for example, if you have an ICMP packet which inherits a quote, you have multiple IP headers inside this field. So of course, when you go for IP source address, you don't get one, but you get two. But that's something you're going to see in one of the next things. So what I usually like to do with this feature is, for example, building a DNS domain list. So if I'm capturing somewhere and I'm interested what domain names are being resolved back and forth either internally or from the internet, that's something you can do pretty quick and easy using T-Shark, because you just give it the trace file and then you ask him, okay, please give me all the DNS responses which contain a DNSA record, and then use Tfields to give me the queried DNS name, which would be the domain asked, and DNS.A describes the IP answers delivered by the server. Okay? So let's do this live. So we go for, let's go for the ring buffer, maybe more fun. So read the first file and check, is there any DNS in there? Yes, we have. So now we go for DNS flags response. Check that again. And you see we only got standard query responses here. But we still have a few C names in here, and we just focus on the A records. That's why we ask before scene, extend the filter and say and DNS response type equals 1, which basically should be the A record. Check that again. No, obviously it didn't work. Resp type 1. Okay, I have to figure why it's not working. Does anyone see the mistake? Yeah, why? So you mean the A record is inside the CNAME answer? Let's check that. So the good thing when you're not sure what it's doing and not sure if the result is correct, you can always go back to the graphical version, just use this filter, put it back in here, and then do kind of an analysis what may or may not have been wrong. So we go for the CNAME here and do what Jasper suggested. So we open up DNS, and inside the answers we see, yes, there's a CNAME, but correct, there's also 2 A records in there. So that's the reason why we got the output also after filtering for A records. Good. So we should be pretty good to go. So then we switch to Tfields and ask for the first thing, DNS query name. Check again. And now we see all the DNS domain names from all those various DNS answers being popped out to the screen, right? So this is maybe what we're supposed to look at. And we also want to have the information, okay, what IP address did these resolve to? And as you know, in DNS, it may be way more than one. So we might not be surprised if we add DNSA. And here we go. So basically, that's a quick one-liner to just give you all the information you need, like was there some problem with any resolvements, or do we have a lookup issue somewhere that an IP address was flapping to a certain domain, or whatever purpose might be there. And also for security analytics, this is one of the default filters we usually do because we want to spot like malicious domain names or known to be malicious IP addresses, and this just gives you a quick and easy ability to run through a gig or a terabyte of trace files, dump you all the statistics you want to have, and print them on the screen. Right? All good up to here? Good. So there's a difference when you use the built-in statistics, because as you may know, there's also the ability to ask T-Shark using the built-in statistics. For example, say T-Shark, please read the first file and do the host statistics. Who knows that? Host statistics? If you do. So apparently, this kind of looks the same, right? So it also goes, okay, this is a German website, resolves to 62 to something, and so on, and so on, and so on. Basically, you can use both. It's totally fair, but there's one important difference between the IP statistics using QZ hosts and the manual way of carving every single information out of the DNS packet. Anyone knows the answer? Educated guesses?
Host you can set yourself.
Once again?
The host's file, you can define your own custom fields.
Yeah, that's also a thing you can do because it also takes into consideration the host field. That's what you can do on the GUI if you want to rename the stuff you see. I'm not referring to that, but let me show you another example if I have that handy here. Nope. This should be it. So let's go tshark, read this file. So as you can see, it's again another trace file where I have lots and lots and lots of DNS responses. And what you may already see is they all give back loopback IP address. When does a system give back a loopback IP address? What does that usually? Sorry, I don't hear. Yeah, sometimes, but there's a perfectly valid reason, and many appliances do this kind of behavior. And this is not always malicious, and it's in most of the cases pretty legit. Any idea? Kind of. So this is basically a lookup using DNS. So they are not interested in getting back a valid IPv4 address or a public IPv4 address. This is some way to do a lookup. So you ask a system, hey, is that information true or not true? And in either of the cases, you get back either a valid address or a localhost address. And this is a thing which is typically used, for example, to watch spam lists. So if you have a mail server running and you want to send an email to a certain external domain, and you have anti-spam stuff on your mail server, he may or may not send those DNS queries to like Spamhaus or other spam list providers and ask them, hey, is this domain known to be a spam sender? And when you get back 127.0.0.1, you know, no, it's all good, right? So this is kind of abusing the DNS protocol to exchange Boolean types of information like true or false, or on which list is it. So in this case, you just get multiple times the same IP address. So if we go for that one and use the same filters again we did before, so we go for DNS, flags, response, and I'm going to shorten that to Tfields, DNS query name, and DNS.a, check for typos. No, it looks pretty good, right? So you can see I have lots of different domains, all resolving to 127.0.0.1. And if I'm just interested in those things, I could do grep 127.0, oops, 0, whoop, 1, oops, did something wrong. There you go. So this all resolved to 127.0.1 and 100. Okay, there's another mistake here. But if you do the same thing with the host statistics, let's do that. You'll see it just gives you one hit, right? So this is the very first hit, and then he says, got my information, I have a match for this IP and a domain name, and he stops counting. So usually when you do a capture, it doesn't make a difference. In most of the trace files I have, it will be the exact same number, both variants you do. But in any case where there might be a double information, which is just overwritten because multiple things give you the same result, that may be a thing where you should not use host statistics. And for me, it's just I by default don't use it since I don't want to figure may or may I not have an issue, so I just go for the plain DNS area and I'm sure every information is in there. All clear up to here? Good. So, for example, let's stick to this DNS example. So now we're going for values. So inside those DNS responses, you get back an IP address, and as most of you will know, you get back also, for example, time to live value. So how long is this DNS answer valid? And this might also be a good thing of interest if you're searching for like anomalies inside DNS, or if you're having connection problems and you're thinking, well, there may have been an issue related to a DNS cache response just timing out and someone had to re-ask the DNS server. So anywhere around that area, it's always a good thought to just check all the DNS provided answers for the time they are valid. And you can also pretty easily dump those statistics out there if you just go for the DNS TTL. So we can say, give us the name, give us the DNS answer, and maybe give us the DNS response TTL. So we can immediately see, okay, we have some domains which resolve to 127.0.0.1, and they have a TTL of 56 or 6 or 60 or whatever. And if we use this on more of a real-world thing, you'll see that these numbers are, of course, way higher. So we go again, DNS, Tfields, address, and DNS response time to live. So there we go, right? And here you can easily spot, for example, that this DNS answer for Google has a validity of 173 seconds. This is 299 seconds. And here you have multiple values. Anyone knows what it is? Well, that's pretty easy because DNS gives you one TTL per answer record. And since you have multiple answer records in here, as you can already see by different IPs, there's going to be different values associated to the different answers. So this is a case where T-Shark is not sufficient because now you would have to go back inside the GUI to check which IP record did have what TTL value. But of course, there's always some limitations. But it gives you a good basic idea what's going on, and you can search for stuff happening there. All right, what's the time say? Half an hour? Good. So another handy thing might be if you just scratch through all your traces you have in network to, for example, spot if you're having MTU-based problems. So as you may know, MTU-based problems, there's a friendly helper protocol named ICMP, which will immediately tell you, if you don't block it through firewall abuse, when there's a connection problem to one side or the other because of a too small configured MTU on one link. And this is something I can really recommend to have just a default T-Shark check running on all your traces you have captured on the edge things where you may or may not have inconsistent MTU settings, and to just watch for those ICMP types where it says, well, we might have an MTU problem, because as long as a single line pops out, you immediately know, okay, there has been a connection attempt from this IP address, to this IP address, and the next top MTU is just 800 bytes, and you right on spot have the problem. You don't have all the big trace chunk data around it, which you basically don't need, because you know between those IP addresses there's an ICMP, there's a problem, and the original packet which did not get through was originally sent from this IP address to this IP address. So if you just reverse that, you have all the information you need. You can immediately say, okay, we got to check this. There's some maybe misconfiguration, or we might have an issue here. Okay, so for analytics, which is basically my favorite part of using the T-Shark, what we're usually tasked is more and more troubleshooting, not plain TCP, because of course it happens now and then that we have severe issues and we love to do that, but more and more we get, let's say, not so big complicated project where it says, yeah, we have some user using a client accessing a web application and they complain it's just slow. Sometimes, not always. So this is, I think, 90% of the cases we were involved with in the last 12 months. So it all comes down basically to response time analysis. So you have a client machine sending a request to a web server, and you just want to check how long did it take for the server to send the response, and depending on the answer, check where does it bring in the delay. So is it the web server being slow to answer, or is the web server querying a database in the back and the database is slow to answer, or. So that's basically following the line. But it always comes down to having the difference times between a request and a response. And for our luck in Wireshark, there's a nice display filter ability which is called http.time. Did you know that? So whenever you take a look at an HTTP response packet, let me show you that here. So let me find one HTTP request. For example, that one. Oh, let's take another one. Not that boring. Well, let's take this one. So in this session, we have a GET request and we have the HTTP response code. And what we used to do all the time is, best practice, you do a set time reference on the request, and then you go like, okay, this is time 0, so we know it was something around, 15 milliseconds until we got the response. Note that down, clear the filter, go for the next request, and check and check and check and check, or sort for delta times or what's or not. So the good thing is, when you take a look at the response, you have this special field down here, which tells you time since request. So this comes in pretty handy because you can just grab this information out of the trace and see, okay, this is my response time. So without having to filter, scrolling again, taking a look, okay, am I having the right response to the right request I'm looking for? What was requested anyway? So this is kind of easy to just check where am I having issues, right? And if you do that, basically, you can do this pretty good scripted. So I should have something prepared in another folder. So HTTP response delays. So we might go for HTTP packets. Let's open that here pretty quick. What was again? Good question. Why do you ask? Anyone knows the answer? Why? That's of the famous TCP Stream Reassembly setting. So depending if you have that in the preferences being set or not set, you will have the first or the last packet of the answer. That's why I have that on the slide. And remember, you can set this using protocol preferences or using lowercase o and force T-Shark to, for example, not use TCP Stream Reassembly, just to be sure. Okay? So we go for all the HTTP responses, and again use Tfields to get http.time. And here you get a nice statical listing of all the HTTP response times, right? And if you're interested in some things being slow, you can do either a live check using T-Shark fired up on the interface, or go through the data called before. And you can say, give me all the responses which have http.time, for example, bigger than 1 second. So every time we're waiting for more than 1 second for an HTTP response, pre-filter with uppercase Y, I want to see this time. How long did it actually take, okay? So when you fire this up, you just see the times where you should be concerned of. So you have one response with 2.8 seconds, 2.9 seconds, and so on, and so on, and so on. And this immediately gives you the hint, okay, that's the bad timings. This is my subjects of analysis, and I'm going to go after this exact sessions where this happened. So what I usually do is after that, I see, yes, there is something. This is why I did the first check, not with all the information in it. I may be interested in, okay, what were IP source and IP destination address of that? Right? Oops, something missing. There. So for this anonymized trace, it's pretty easy. So we all see there's a problem between those two IP addresses where we have some type of issue where the HTTP responses take, for whatever reason, pretty long. So I can do a next step and say, okay, give me the TCP stream ID. Because then I exactly know on what to filter in the GUI, and I only have to look for that specific TCP stream where from pre-looking on the CLI using T-Shark, I already know this is the TCP sessions where I have problems, and I don't have to go through the whole trace and analyze if there's something bad because I already know it. And so now we can, for example, directly jump to TCP Stream 66 in the trace, and then start for the first time looking in the GUI what may or may not be wrong. 66. Let's filter it. There we go. And as you can see here, here's an HTTP 200 OK. Time since request 2.8 seconds. So we're right on spot on the problem without having to go through various hundreds of sessions to see if there is a problem, because we already did the pre-checks using the CLI. Okay? So in case you're interested why it took so long, stay after the talk and we can have a discussion about that. But it's currently not the focus. But my aim was just to show you can make your life pretty easy by pre-filtering things which will pinpoint you to the exact spot-on trace. And as you can see down here, now we're talking of 780 packets out of a 144,000. So imagine you're scrolling through 140,000 packets searching for some error which you won't find. So make T-Shark do the work for you to pinpoint you to where might be problems and verify them using the GUI. That's like that. And of course, now you would have to do this for all those streams, but fair enough, that's what you do. So, lucky for us, we have HTTP time. Now, when it comes to encrypted traffic, situation's getting worse, right? So when we see HTTP request, HTTP response, and we have HTTP.time available. So something pretty nasty is when you don't see what's going on inside the traffic, either because it's encrypted or it has been anonymized and the whole payload has been cut off. So let me see if I have an example of that here. Let me check. Yeah, HTTPS. So you can see this is a pretty huge trace, and this is one of the projects we did last year. And it's just a very small snippet where we know there was an issue. So this trace should be around 1 million packets. Let me check. Yeah, 822,000 packets. And the problem description was something is slow. Okay? And then you go here and say, okay, what's being used here? Yeah, SSL, TLS. So all this stuff in here with close to zero exceptions is completely encrypted. So who had ever had the fun to do troubleshooting on encrypted traffic? Yeah, did you give up or what did you do? You can't do much. That's the thing. You don't exactly know what the protocol is supposed to do. So the only thing you can do is give your best educated guess of what you think may be going on and hope that this is correct. But there's one thing you can always do with encrypted sessions, and this is again going after timings, right? So if you know basically what's going on behind that, so if someone tells you, yeah, this is an application which is requesting something via HTTPS and it's getting answers and requesting and getting answers, you know it's going to be like request, response, request, response. So you may have an idea on what to look for. So you're looking for requests, which you can't read. So you have to figure what's a request. And at some point later, you get data packets back, which you again can't read, but you have to figure might be a response. So with HTTPS, it's pretty easy, since when you know who the client is, you will see he will send some bytes to the server at some point. And when the server, after a certain period of time, sends chunks of data back to the client, you have a pretty good guess that this might be one request followed by a big response flowing through several packets. Okay? And so this is the idea behind that. So you can basically do the same approach with HTTP time, but you have to rely on another filter to do that. This is tcp.time_delta. So this is a kind of interesting field because this gives you the delta time not of the last packet in the trace, but the delta time to the last packet in that specific TCP conversation. So it takes ages to process for T-Shark because he's having to look all the data times for every single TCP stream inside a trace, which may be thousands or 10,000s. But when you say we have a delay in the same TCP session, which is bigger than a certain threshold, in this example 1 second, please pop out the exact packets where we have that. And then you have two choices left. So either it's the user sitting there not doing anything and after 10 seconds, for example, saying, okay, I need the next page. Of course, then you have usually 10 seconds delay because this came from the user. But if you have, as a next step, focus on the data from the server to the user and say, okay, when did the server send a data packet after a huge delay after he got something from the client? Then you definitely have something because the server in HTTPS usually does not send packets by himself which were not requested. And this can be a good approach to troubleshoot everything which is inside encrypted channels, especially with bulky transfer as within HTTPS, right? And since we're lacking a little time, I'm right jumping to in this trace, and we're going to follow TCP Stream 16 on frame number 1256, for example, just to verify. So 1256. So what do we have here? I'll filter that. And you see, this is already taking 10 to 11 seconds. So if I'm not knowing what I'm looking for and just blind filtering through the whole trace to see if I spot something, you can imagine you end up having hours. And here you see one packet of application data, which has a delta time in that conversation of over 1 second. That's why it matched the filter. So this comes from the server, and what do you see before here? You have the client sending something. You have the server sending the ACK pretty fast, and then it takes 1 second before the first data packet arrives. So even we don't see what's inside there, even if we don't see the request and we don't know what was requested, we can definitely say, yeah, here's a problem. So something is delaying the response for 1 second. We can't tell if it's the server itself, if it's the back end behind the server, if he's going to fetch information from other systems, which may bring the delay. But we can already verify the problem and say, yeah, we can understand the users are complaining because we clearly see something which is feelable by the user, because 1 second delay definitely is something users will recognize. And again, searching that by scrolling up and down takes me ages, gives me a hard time. I think even for Hansang, it might not be that easy to just scroll through and spot these things. So this is the examples where I can just recommend make use of the CLI, bring that up, focus on the stuff you need to check because you know it's in there and you just have to spot the right thing. And here in this example, you get the stream number, you get the exact frame number, which has a defined problem. So all you have to do is from that very frame, take a slight look back in time, what happened before and what happens next, and you can directly go to analyze this specific situation without having to find it first by scrolling, by whatever. Okay. Quickly set the time, 10 minutes. Okay. So for the last example especially, if you just filter for certain problem indicators and let it pop you out the stream numbers, TCP stream numbers, you can also do something to pre-do all the work. So when you're getting back to thousands of trace files, you can do a for loop which filters all the streams which contain indicators of errors. So it might be retransmissions, might be time issues, whatever. And if you just pop out those stream IDs in a text file, you can just do a second Tshark run with this file list and say, Tshark, please extract me all the TCP streams of my raw data where I already know we have, for example, retransmission problems or where we have timing problems or whatsoever. So after those two stages, you end up having dedicated traces for every single TCP stream which will have a problem inside. And then you can just one by one go through all the already pre-filtered TCP sessions, and in every TCP stream you will have that one thing to analyze. And you can, for the first part, ignore the rest of the data. Good. So this is basically how that works then. So you pipe all the TCP stream results into a text file, and then you say, okay, for all these numbers, jump back into the data and please filter TCP stream number 154, 137, 160, and so on. And you will get a new output file which is named error stream underscore, in this example 154, or error stream underscore 137. So you have that ready to analyze. Okay. So any questions? The question was, if you spot one packet using Tshark, do you have to open the whole thing in Wireshark to be able to see the next five packets? Yes, there are. You could just go for the frame number and say frame number is greater than and smaller than, and give that to you. But I usually go to Wireshark because I'm more interested in the dissecting information, and that's definitely something I'm not doing on the CLI. Right? So I'm just using it for indicating problems and usually switch back right after that. So for the end, I wanted to give you a very let's say, not so real world example, but something we actually also did, because I once did a packet loss analysis completely with the CLI, so I did not look at all into the graphical interface, but I didn't want to do this, it just happened to come out by chance, and I thought I'd give you that just as last example of some exotic way to pre-troubleshoot any problem. So I have a trace where there's definitely packet loss in there, and I use the default strategy like you have seen in Hansang's talk this morning, like TCP analysis flags. I took one more step to directly go for TCP analysis retransmission. So I said, give me all the retransmitted packets in that particular trace file. And I don't care about that. I just want to see which stream contains a retransmission, and then, as before, filter all the streams out. So that was me thinking what I might do as an approach. However, it turned out to be, and I will show that quickly live, that this packet dump contained so much retransmission, so much packet loss. I said, I'm not going to go through like 100 sessions and see what's going on. So I thought it must be a major problem if we have basically every session is intensely affected by packet loss. So let me quickly see how this looked. So this is the packet loss, and we're going for TCP analysis retransmission. And you can see there's hundreds and thousands of retransmitted packets. So we are really having issues. So next step was, hey, I want to know which TCP sessions are affected to filter them later. So we go for TCP.stream. And then we see, whoa, lots of sessions. So all those different TCP sessions have packet loss problems. So that's what I wanted to say, okay, which session do you now take? On what do you focus with your analysis? Well, I take the big things first, so I decide I go for the session with the most packet loss, because if I might find the reason for that in there, it may just be as simple as this is being the same explanation for all the other sessions having issues. So I went to just sort this, make it unique, and sort it descending with the worst guy being on top, wait for it for a few seconds, and there you go. And you can immediately see, with just a quick one-liner, you get the information that TCP Stream 0 has 212 retransmission, and TCP Stream 254 does have 194 retransmissions, and then the numbers rapidly go down. So obviously, it's two sessions which are mostly affected by all this stuff, and then we have a big scatter with just between 10 and 20 retransmissions, which affect various sessions. But those two candidates from pre-checking are the two sessions most interesting for me personally. So the next step would be, of course, to go for TCP Stream 0, which is the top scorer, and then get additional information like, okay, what's the IP source addresses in here? So who's affected and in what direction do we have the retransmissions, right? Because this may or may not be completely equal, or maybe one-sided, that you only have packet loss from one to the other side, or the other way around, which again might give you another indicator of what might be going wrong. So when you do that, and you go for Stream 0, and you go for this analysis. So this should work. So from just looking at it, you see this 8-point-something address is way more affected. So 8-something is retransmitting way more packets than the other one is doing. It's just a few in comparison, and they both add up to 212 retransmissions inside a single session. And now using that, you can check the ACK numbers. Because you want to know, is it really retransmission or just having a Wireshark bug or an itch, or is it out of order, wrong flag as retransmission, or what may or may not be going on, or may this be even a keep alive flagged wrong. So I just thought, okay, let's just take a look at the ACK numbers. And who's been in Hansang's talk this morning? So you will see something which might or will hopefully be pretty pretty known to you. So we use this thing, and we say the packets should come from this 26 something IP address. Let's check, did it work? Looks good. But instead of IP source, we want the TCP ACK. There's something wrong. I didn't figure source. Sorry. Source. So this should be a pretty short list and should be consistent. There we go. So what you can see is we have retransmissions inside that stream from this 26 something IP address. So he's sending data all the time, but with every retransmission, his own ACK number is increasing. What does that mean? That means between the retransmitted packets, he did successfully receive data from the other side. So basically there was some type of flow, and I'm not dealing about the reason for the retransmission. I'm just trying to figure out what may there be in general going on the wire. So if we change that, say, okay, now we focus on the other guy, so on this 8 something IP address. We do the exact same thing and take a look at his ACK numbers. What do you see here? So the ACKs are pretty consistent. Is that a problem? Not necessarily. He may just be the sending guy. Because if he doesn't receive stuff, he doesn't have to acknowledge and he doesn't have to increase his ACK number. But we see lots and lots and lots and lots of retransmissions from this guy. And then we see that the ACK number changes somewhere. So we had obviously gotten something new as the request, and again he's sending and retransmitting and retransmitting and retransmitting and retransmitting, and again and again and again. And this pattern just stays the same. So we have huge retransmissions with the same ACK number. And while this may be the case, it's still rather unusual, except for having one big download, which just takes a long time to deliver. But this just caught my attention. When you take a look in the original trace and go for that thing, you'll see that something interesting is going there. So now we take the same filter, do it, and this is how it looks in the GUI, right? And so what do we see with the sequence numbers? Right? So we have bulks of the same packet being retransmitted all over again and again and again, and then at some point there's a new packet and a new packet and a new packet. But if you take a look at the sequence numbers, they're tiny. You see that? Here's little big data and there's tiny packets all over the place. So if you do a conversation filter on that, you see something pretty interesting. Do you see IP source and IP destination? It's always just the IP address 8 something sending. There's no ACKs coming back for what not reason. So if we go before that happening, you see here there's regular conversation. But out of one point, here's some piece of data coming back, and from that point, time reference, you see that? There's just one-sided connection, and here after 3.8 seconds there's the first packet coming back from the other side. So what was that clearly? Either host not available during that period or linked down. And when you go back to the other things where you saw all the other streams are also affected, we'll see the exact same thing for other two IP pairs, and you quickly see, okay, classic link not available through that situation. So all clients from one side were just blowing packets to the wire. They did never reach the other side, and you had the 3-point-something seconds link outage on that. That was why I just out of total coincidence troubleshooted that sticking to the CLI, because I thought that, well, this ACK patterns is quite unusual. So like I said, not planned, but rather something exotic where you may also have a quick win using that. Okay, so if there are any questions, feel free to ask them. Even after this talk, I will stay here for as long as you want to talk to me. And otherwise, I hope you enjoyed that, and thank you very much.